Hello, everyone. For those who don't know me, I'm Yulu. I'm postdoc at CAPAC. So here I'm going to make a presentation on a theoretical model to understand galaxy formation in low mass halos, which is a different regime from the previous talk. And the main focus of this theoretical model is to understand galaxies, especially disk galaxies, and they are hosted by low mass halos, and they are still star forming. So the outline of this talk is, first I would like to show several outstanding problems. And my goal is to convince you those are real problems, and we got to solve them. And then I will throw out a new model, which I call preheating model, and to see whether we can solve those problems and what the implication of these models is. And first outstanding problem, I think, is to understand very tight stellar mass halo mass relation and cold gas mass halo mass relation. There are a lot of observational data through complicated or empirical modeling to indicate actually the stellar mass to halo mass ratio scales with halo mass with this characteristic scaling relation. In particular, for low mass systems, the stellar mass decreases rapidly with decreasing halo mass. And that means the baryon in low mass halos just not simply in stars. And more interestingly, people have done another exercise using 21 centimeter detections for those cold gas galaxies, and they find the cold gas mass halo mass ratio also decreases with halo mass in a similar way. So that means the baryon in cold phase is not in stars or in cold gas. So where the missing baryon is, that's the first question. We have to understand this very simple scaling relations. And so very early on, people realized in order to understand the decreasing stellar mass halo mass ratio as function of decreasing halo mass is to invoke a strong feedback. So because the low mass halos have a shallower gravitational potential, if you have feedback or either supernova feedback or radiative pressure, so you may just unbound baryon, and those low mass halos can end up with low baryon poor situation. So those models normally starts with all halos accrete baryon follow dark matter, and the baryon mass fraction of all halos starts with cosmic baryon fraction, and then you start to have star formation and throw out actual baryons. But actually, those type of models are very difficult to make a consistent pictures. So first of all, even you can tune the model to match the stellar mass halo mass relation for Milky Way size part. The low mass part is still deviating from observations. And more strongly, if you make a prediction for cold gas, actually the inconsistency is even stronger. And also, in order to make the model consistent with those observations, you actually need very large loading factor for those feedbacks to be effective, simply because low mass halos effectively cool baryons, and they are not in cold phase, so you have to throw away. So this large loading factor is basically required by those observational facts. And the second problem is the number density evolution of low mass galaxies. Actually, this is just the other side of the previous problem, simply because low mass halos in CDM, low mass halos form quite early, and they can efficiently cool gas. And then you predict much higher number density of low mass galaxies compared to observations. So those are a number of different semiotic models or hydrodynamic simulations. All these models, even you carefully tune to match redshift 0, they still over-predict the number density of low mass systems at higher redshifts. And this is my broader model family using symmetrical model and constrained at redshift 0. So using posterior probability distribution to make predictions for high Z galaxies number density. So my exercise basically confirms the previous finding. And the third problem is the size-stellar mass relation. And different from previous talk, here what I'm looking at is star-forming disk galaxies. And the y-axis is the half-mass radius of stellar disk, and the x-axis is the stellar mass. And these panels are for redshift 0, 1, and 2. And all these different lines are different observational measurements, although there are quite amount of inconsistency among observational data, but you roughly see this type of trends. And the black dots are theoretical model. If you simply follow the ejection model, which you collapse baryon and you rely on feedback to throw baryon, and you predict a much lower size of Milky Way size galaxies. And if you go to higher and higher redshifts, this deviation is even larger. So this problem is pretty clear. And I think this is a nice paper to illustrate why this is the case in lambda CDM. This is where Milky Way stands in this diagram. The y-axis is the specific angular momentum of the material of the Milky Way and the mass of the galaxy. And the dashed line shows this relation of dark matter halo. So if the Milky Way has a specific angular momentum of the dark matter host, the galaxy would sit in this spot right away. However, symmetrical models or simulations normally predict a much lower specific angular momentum of the baryon when you really look into the central objects. So this is shown in this shaded region. Why is that? Because the mass distribution of dark matter in the halo follows this line, but the specific angular momentum of the matter follows this line. So this basically says the angular momentum, the high angular momentum material is simply distributed in larger radii. But when you cool material in the central region, you basically bring in low angular momentum material. And the disk, even you conserve the angular momentum, you still predict a compact disk, which is very different from observation. So these are the real problems in galaxy formation models. So here I'm throwing another type of model, which involves preheating. Here I argue if you have another situation where the intergalactic medium is simply preheated to a finite entropy, so the thermal pressure of the baryon will prevent the baryonic matter from collapsing into low mass halos. And this is exactly what I showed in a few years back using hydro simulations. And if I define entropy as this, and zero entropy of a halo as this, zero temperature and zero density to this power, then you find if you preheat the intergalactic medium to an entropy higher than the zero entropy of the halo, the fraction of baryon can collapse into the halo decreases rapidly with the increasing entropy of intergalactic medium, or the ratio of intergalactic medium to the zero entropy of the halo. So in this situation, if you preheat the intergalactic medium uniformly, you would prevent baryon from collapsing into low mass halos. And there are other consequences I will show later. So based on this argument, I start to try a new model, which consists of all the essential parts of normal symmetrical models, which are widely used in the field. But I have more detailed treatment of how gas cool in dark matter halos and how gas is distributed in the halo, and also the angular momentum distribution in the halo and how the gas cool to finally settle in the central disk. And also I used recent star formation model to follow where star formation happens in the disk and to make a prediction of the final disk. Here I show the basic prediction. This is at redshift 0, the stellar mass fraction as a function of a halo mass. Those dots are just randomly chosen halo mass equation histories. And this is the cold gas mass fraction as a function of halo mass. So, and very interesting to emphasize here is in this model, I don't include any strong feedback in the late time evolution of all the galaxies. And simply because the preheating can prevent baryon from collapsing into low mass halos, I can naturally get those predictions. And also, these are the star formation rate histories for different, here I just show different halo masses. One is 10 to 11 solar mass halo at the present day, and the 10 to 12 solar mass at the present day. And the cyan bands are from Peter's empirical model, and this preheating model can naturally reproduce this trend. And more interestingly, for low mass galaxies, because I don't need to involve any feedback, so I can keep those low mass systems still star forming even at late time. And another natural consequence of this preheating is because you preheat the intergalactic medium, so the baryon has a higher entropy than the zero entropy of the halo. So then when the baryon collapses into the halo, you don't expect any gravitational shock. So there is no shock in low mass systems. Because there is no shock, the final hydrostatic configuration of the gas is completely changed. Here I'm showing a hydrostatic equilibrium solution for isentropic situation where the entropy is flat. And this is isothermal case if you assume baryon collapse into halo and shock heated to zero temperature. So you find that the density distribution of this isentropic situation is very, very flat. So that means most of the baryon actually is distributed in larger radii. While in the isothermal case, which is normally adopted in galaxy formation model, has a very concentrated hot gas distribution. So this is why in this situation, you always cool baryon from inner region, and the material has much lower angular momentum. And in this situation, because the baryon is more extended distributed, you would expect when cooling happens, you can bring in higher angular momentum. And this is exactly the prediction. Here I show the specific angular momentum divided by specific angular momentum of dark matter and how this quantity is distributed as a function of radius. And because this isentropic or preheating case has gas distribution more extended, you bring in a lot of high angular momentum material. Here I compare the disks at redshift 0, 1, and 2 in these two different model families. And in isothermal case, the model predicts a much more compact disk for all the phases, stellar phase and the cold gas phase. And in the isentropic case, you predict a much more extended disk all the way back to higher redshifts. And this is the final prediction of half mass radius of the star forming disk at redshift 0, 1, and 2. As I said before, because this model has much extended hot halo gas, so the cooling happens preferentially at a larger radii. And those materials simply bring in higher angular momentum and bring those points up to the value where observations suggest. Here I simply flash between those two model families. Then you see this preheating works much better than the conventional model. This is my summary. So here I hope I have convinced you those are outstanding problems. And Of course, there are a lot of suggestions by changing recipe of feedback. And from my experience, I feel feedback sounds plausible, but it's actually very difficult to do, simply because you require very high loading factor, and a lot of physics are not really well understood. Here I'm highlighting this alternative model family, which has very clear model predictions, and hopefully this is interesting for us to think about and to test. Thank you.
Yeah, so the key question, of course, is where this entropy came from, and you give several possible explanations there. But I noticed that some of them are very spatially intermittent. For example, if you have early starburst galaxies, then there would be regions where that's essentially a feedback mechanism that'd be located there, but there'd be vast regions of the IGM which would not be heated. In the case of the pancake formation, that depends upon if you're forming a cluster of galaxies, that works, but if you're out where the Milky Way is, it might not work so well. So could you comment on how such a mechanism might work in typical parts of the IGM?
Okay. So first of all, the model I show here today is just a typical situation. Of course, you expect a very large variation. And you are right. Exactly, this model implies very strong location dependence. And for a number of mechanisms which could be responsible for this preheating, I would agree, actually, some of them are only effective in the region where you have early bursts or pancakes. But because the focus of this model is for low mass systems, and it's true, actually, in simulations, you see most of the low mass systems are embedded in pancakes. So if you have a pancake formation and the pancakes could shock heat the baryon, so that could substantially change the formation history of low mass halos embedded in those structures. And certainly those location dependence can bring in scatter of this model.
Yeah, I guess I'm sort of jumping a little bit on the same point. I mean, if you put in a lot of entropy, right, if you do it at high redshift to too large an area, you're going to not get the laminar alpha forest correctly. So you can't have them one too hot. So, I mean, have you thought a little bit of how, because you have all the parameters now that you would sort of need to get the galaxies right, of how you'd play with simulations to sort of include this source term to confirm, that the semi-analytic predictions would hold in the
actually, H alpha is an issue, but actually some of the model demonstrate actually you need to lower the number density of those type of systems. So in that sense, this type of model may help even. But it definitely is interesting to take into account and constrain the model and see where the situation is. As normal, there are a lot of degeneracies. Here I'm just creating another dimension of the model. Certainly some existing thoughts are totally degenerate with this. But here I'm just highlighting very clear predictions of this. For example, you expect low X-ray halos in Milky Way type halos and even lower. And also you don't have any shock. All these things could be tested. And I'm very interested in next step to come back to my Bayesian constraint inference type of thing to understand the degeneracy in the extended model family.